Every chatbot has a hard limit built in. It can't read ahead. It writes one word at a time, left to right, blind to what's coming next. A new kind of model just broke that rule, filling in a blank using the words that come after it, and researchers found the exact circuit that pulls it off. The thing doing the copying has a name, an induction head. Think of it as sticky notes. Every word gets a note recording the word that came just before it. When the model meets a word it's seen already, it hunts for another place carrying the same note, and copies down whatever sat there. That one trick is a big part of how models learn from examples inside a prompt. And in an ordinary left-to-right model, it only ever runs backward, because the sticky notes only record the word on the left. Diffusion models work differently. Instead of writing one word at a time, they start with the whole passage blanked out and unblank it in passes, so every gap can see words on both sides of it. Andy Katruna and Emilian Radoy at Politehnica Bucharest trained matched pairs of models, same architecture, same data, one left to right and one diffusion, then gave both a purely structural test, a random sequence whose first half repeats exactly in the second half. Both families show the same abrupt phase change, nothing at all for thousands of training steps, then the circuit snaps into place. One-layer models never get there, two layers and up do. The diffusion models reach it earlier than their matched counterparts, and the score peaks about 150,000 steps in rather than climbing forever. But an earlier, higher score doesn't prove a better mechanism. It might just mean an easier problem. Inside, the circuit is a two-step relay. In the first layer, one attention head tags every slot with the word on its left, and a second tags it with the word on its right. Out of 16 heads in that layer, exactly 2 matter. In the second layer, induction heads match those tags against the same tags elsewhere in the text and pull that word into the gap. Knock out either one of those two tagging heads, and the model's induction score drops by about 2.1 nats, a log probability score the researchers call the induction score. Every other head in that layer costs less than 0.6, and the circuit is direction symmetric. Forward and reverse scores sit on top of each other for the whole of training. It copies from the future as readily as from the past, because nothing in the matching rule refers to the direction of time. Which sets up the question this whole paper turns on. What happens when you take the future away? So they controlled exactly which neighbors around the gap were visible. Left only, right only, both, or neither. That isolates what bidirectional access is really contributing. And here is the result the video exists for. With both sides visible, the diffusion model scores about 4.4, comfortably above the left to right baseline of 3.46. Now cover the right-hand side so both models see exactly the same words. It falls to 2.23. That is below the baseline. Given identical information, the diffusion model is worse. The advantage was never a stronger mechanism. It was a wider view. There is a second finding, and it is the strangest thing in the paper. These models were never given a time step. Nothing tells them how far along the unmasking process they are. They built one anyway. Probe the internal state, and you can read off what fraction of the entire page is currently blank, with an R squared above 0.8, and that information shows up immediately after the very first attention layer. As more of the page gets hidden, the model's predictions grow measurably less confident, even when the words right around the gap never change at all. The caveats are real. These are tiny models. 2 to 3 layers, attention only, no feed-forward blocks, trained on synthetic random tokens chosen to strip out meaning. The circuit analysis is done on modified versions of the trained models, and whether any of this survives in a full-scale deployed model is completely untested. So here's the real takeaway. Diffusion models don't have better copying machinery. They have a wider view. When you can anchor a guess from both sides of a blank instead of just one, you find the match more precisely. The advantage is real, and it comes entirely from being allowed to look both ways, not from a smarter circuit. So the next time someone tells you diffusion language models are just slower chatbots, you know what they can actually do that the others can't, and just as usefully what they can't.